play you some kind of hold music, but it's probably not my greatest talent, so I shall simply give it another 30 seconds or so. Yes, if you've just rolled in, it's going to be just a short while to settle while Zoom lets the participant count all the attendees into the rooms and gets everything set up on YouTube. So we'll be kicking off in almost 10 seconds, because the logistics will be the same as last week. That will be just a little segue in. To remove the turn off the camera sign. This is being delivered. Normally, this is something we put up when we do training for private sessions where we don't use the webinar framework and we encourage people to ask questions verbally. So that logistics was just incorrect for this session where you can't turn your cameras on and off anyway. So the fact that you're being recorded should not be too much of an issue because you won't be speaking or putting yourself on camera. So yes, these sessions will be recorded. That means that we'll share videos after the session to all the registrants. Questions are welcome. You can put them in the chat. I have got my box open this week, so I'm likely to see them as they come through. I have also got the Q&A box up, so if you use the "This is really a question" button, it will pop up in a different window for me. I will try to do questions briefly during the material and expand on anything that has a long-winded explanation at the end. If you post on the chat, we have somebody in the background helping me who can repost links to the slides and things like that as you need. So that should pop up now if you haven't got it in your current chat window. But that will give you links to today's slides and to the other components that we need. Okay, so we're going to look at the various Linux schedulers, including the real-time schedulers. As we kind of promised last week, we're going to look inside the kernel. So this is the same slide that I put up last week, introducing the whole idea that real-time is as fast as possible. No, it's not as fast as possible, it's as fast as specified. And the section in black is what we're covering this week, the different ways you can tweak the kernel to trade off between system performance and worst case latencies. And just as a reminder, again, we have our little example real-time system. We won't lean on it nearly as much this week as we did last week, because we're looking inside the kernel. What it's actually doing in terms of the real-time system that we've had as an example is much less important, but we will still refer to it occasionally. And just a reminder before we start about Linux user space, this is what we covered last week. Linux user space always runs with interrupts unmasked, and Linux user space can always be preempted at any time by a higher priority process or thread. Regardless of how you configure the kernel, the user space is always interrupt unmasked, which means it has essentially no interrupt latency, and it's always capable for it to be preempted at any time. However, what user space can do, of course, is make system calls. And when it makes system calls, you're no longer running in user space, and these rules change. And that is essentially what today's talk, when we're talking about real time, will be about. It's the fact that because you've gone into the kernel, those rules change. But while you're running regular user space code, your compiler is running compute intensive stuff, you're running a big ray tracer, you can be preempted at any time. It's not using compute power that causes any kind of latencies or delays. It's making system calls and going into system activity. So we've had this kind of little wheel up before showing the various aspects that we've had. We talked about memory management last week. There's not a great deal in kernel to follow up on that, but the scheduler we do need to look at in a bit more detail today. So, I mean, the job of a scheduler is simply to treat the CPU as a shared resource and allocate that to competing demands for the resource in order to meet either performance, real-time, or perhaps power requirements. And the major factors to the scheduler that we're going to be caring about is a mixture of strategy, the occasions where we can make scheduler decisions, and any metrics or algorithms that help us implement the strategy. And the strategy is just the high-level view. In the case of the real-time, it means the real-time scheduler, it means the highest priority task is the task that's on the CPU. When we're talking about CFS, we gave a vague idea of fairness when we were talking about it last week. We'll drill down a little bit deeper into what the strategy actually is. And then we'll see algorithms that realize it. So CFS's fundamental strategy is to try and act as though all the competing tasks had individual CPUs, and therefore when they require performance, they get it. And then the fairness comes in when it can't meet that goal. Scheduling occasions, I will quite often verbalize this as the scheduler being called upon to make a scheduling decision. So it's the point at which the scheduler has to decide whether to preempt or not. And it follows that when you're called upon to make a scheduling decision, that you're allowed to preempt at that point. Otherwise, you wouldn't be called upon to make the decision. And then finally, we have the actual underlying algorithm and some metrics that it may be using to tune itself or make it effective. So as we discussed last week, there are three primary scheduling strategies we can adopt in the Linux kernel: the CFS, sched, other, the real-time scheduler, and the deadline scheduler. We also mentioned two other scheduling classes that Linux has. It has a scheduler called stop, which is used to bring CPUs to halt when you're doing hot plug activity, and it is the highest priority scheduler in the system. So if the operator of a system directs that a CPU fall out of use, that is the most important thing that CPU can be doing, is trying to stop itself. At the other end, the least important activity is going idle. This is itself a special scheduling class, and it will essentially be then at that point running code whose ambition is to conserve power as much as possible, or in the worst case, do nothing. And that's the least important thing we can do, because if there's work for us to do, we don't want the system to go idle. So we have the reminder here of the mapping between scheduling classes and scheduling policies. The key thing about these two new scheduling classes we've introduced, stop and idle, is they do not have policies because they are not accessible to the user space. The policy is immaterial. They just are scheduling classes that could have work to do or no work to do. The other scheduling policies are the things that we toured last week, with the reminder that because we're looking in the kernel now, we might well see shed normal as the name for the default CFS scheduler, rather than shed other, which is what it would appear as in user space. That's just a historical behavior. Shed other, I believe, is the POSIX name, and shed normal is what the internals of the kernel chose to call it. So just, I mean, the idea that these scheduling classes are some way magical, I just want to dispel that idea. You can see here the inner core of schedule is simply a loop that goes round the available classes, trying to find one that has a task for us to run. And because idle is the least important class, the last on that list, if you've got through the other four classes and you get to idle, it will find something for the CPU to do, which is to go to sleep. So there's nothing, impenetrable or even that hard to read going on in this code. So I suppose the best reason we put this on display is to say the scheduler doesn't have to be a scary thing. It's not. It is quite readable code. It is ultimately walking lists and trees and other classic computer science data structures. Obviously, tuning it can be a challenge because you've got to balance lots of competing needs. But reading and understanding it is not a really difficult task. This is picked out as being, it is quite readable. You can see what it's doing. And then finally, to talk about some of the measurements. So we talked about measurements that inform scheduling decisions. So there's two particular measurements we wanted to introduce at this stage. So we've put up a system which is a task that is waking up and becoming runnable, and it's on a 4 CPU system. So some of the decisions we might have to make, particularly on SMP systems, is where that CPU is going to execute. Sorry, that task is going to execute. Which CPU do we add it to the run queue of? That's usually made when a task becomes runnable, when it stops sleeping. At that point, the task will be put in the run queues. It will either take up an idle CPU and start running immediately, or it will be put in one of the run queues for one of the CPUs. These run queues have been drawn as linked lists. They are not for all scheduling classes linked lists, but drawing them as ordered trees is rather diagrammatically difficult. So we've visualized it as a linked list now, but in all cases, it's going into a sorted list that we can traverse quite quickly to find the next task. So first decision we have to make is which one it's heading towards, and the major influence of where we choose to put it is something called per entity load tracking. So load tracking is an attempt to estimate how much of the CPU a particular task will consume. So something that sits there idling, waiting for events would expect to have quite a low load because it spends most of its time asleep. Something that is blitzing the CPU with compute intensive activity would demonstrate quite a high load. The final metric that is used for some of the schedulers is a thing called vRuntime, which is little more than the amount of time a task has spent on a particular CPU executing. So this is time not on the run queues, but time executing. And that can be used to obviously balance up fairness when we're trying to write fair schedulers like the CFS scheduler. So per entity load tracking is basically tracking when tasks are running and when tasks are sleeping. It is distinct from the virtual runtime because it decays. And so if a task sleeps for a very long time, its load will eventually decay. And it's allowing the CPU to try and figure out what fits onto particular CPUs. Where you've got a CPU that's lightly loaded, we can figure out that it will fit on there. And it's used for other power related decisions as well. So PELT is not just for SMP load balance, but the power related things that it can be used for as well don't come into scope in this course, except as a hazard, which we'll discuss right at the end. So with those concepts, particularly the vRuntime we want to look at now, we can start to think about the completely fair scheduler. So the fair scheduler was introduced. We didn't actually track a date, but it's been here for quite a long time with this. It was heavily influenced by a scheduler, a research scheduler that came before, the rotating staircase deadline scheduler. And its goal is to be fair. It replaced a scheduler that was full of heuristics. A scheduler that used to try and spot interactive tasks and give them a dynamic priority boost so that your editor or your mouse or anything else that had to react to things ended up with a slightly higher dynamic priority than things that were compute intensive. And it replaced this kind of set of heuristics with some fairly rigorous maths about being fair that actually gives us a result that is comfortable and sensible for a large majority of our workload. It's built around this concept of vRuntime, and the essence of it is the task that has had the least vRuntime is the most important task to run next, which makes sense. A compute intensive task will sit there gathering lots and lots of vRuntime. And if an interactive task wants to run, it won't have consumed as much vRuntime. So that means that the interactive task that becomes runnable is going to be the most priority thing on the system, and it will preempt the compute intensive task that was dominating the CPU when it needs to. That gives us that comfortable, pleasing interactive behavior. And in this case, without ever having compromises that can penalize the compute intensive task. The compute intensive task is also guaranteed to get a fair slice of the CPU if a interactive task wakes up quite quickly in a short burst. The reason we'll talk about this as vRuntime rather than true runtime is because the task's nice value is essentially a weight that affects how fast tasks accumulate virtual runtime. So with a higher weight, we'll get a much slower increase in virtual runtime, and a task will get a larger slice of the CPU. There is one nuance to this. So vRuntime for newly added tasks. This is tasks that are either created for the first time, or indeed for interactive tasks that have been sleeping for a very long period of time. And that is that if you've had a compute intensive task that's been running for 3 hours already, and you start a new task, that obviously you can't then block the compute intensive task for 3 hours while the other one catches up. So the other thing that's happening under the scenes is a concept called the min v runtime value. It's a monotonically increasing value that tracks the smallest permittable v runtime. So if a new task is created, it doesn't get a runtime of 0, it gets a runtime that is the min v runtime. Likewise, if tasks are asleep for a long time, then when they are made runnable, we compare against the min v runtime and boost their runtime up. So that they will still be at the minimum, which means they will still be very near the front of the queue to run. But when they do accumulate runtime, they will then compete fairly with the compute intensive tasks that have been running for a long period of time already. Just to give you even more view under the covers, so CFS is managed as a red-black tree, which is a type of sorted binary tree that has some quite pleasing complexity properties of insertion and deletion and search. So it self-balances, and pretty much every action you choose to do is a log n complexity. So yeah, log n complexity. So there was some fuss about the kernel schedule at one point, and there was a lot of effort to make it 01. And that was the heuristic schedule that I mentioned before. But unfortunately, the compromises involved in making an 01 scheduler are that you can't run any of these complex algorithms. And that means that the heuristics can then create unfairness, which means even though it's 01, if you're not doing the most important thing in the system, it doesn't matter how fast you chose to do it. So the scheduler was at that point changed over to a log n complexity scheduler. So when you're called upon to make a decision, the complexity is related to log n of the number of tasks. So this is a tree ordered by the v-runtime. And in this case, it is the leftmost task that will always get picked. So this does essentially create an order in which tasks will run. And we can add tasks to it, remove tasks from it, and find tasks relatively cheaply because of this self-balanced tree property. Red-black trees themselves, it's an interesting bit of maths. If you're into computer algorithms, go and read the Wikipedia pages and some of the other material about them. They are interesting, but if I just tell you that they are self-balancing and log n, you can understand everything you need to know about the scheduler. Digging into the nice value at this point. So last week I gave you the standards view, which is if you have a negative nice value, you are strongly favored. And if you have a positive nice value, you are disfavored. But I didn't give you any units. I didn't tell you what it meant to have a nice value of 19. So we can look at this now. Now we're looking at the implementation, not the standards. We can find out what Linux actually does. And it introduces this idea of a 10% change for each nice level. So the idea behind this is if you've got two tasks competing with the same nice level, they should get a 50-50 split. If they are competing with one at nice level n and one at nice level n+1, then you get this 10% delta between them. The one with the nicest behavior will get 10% less CPU than would be its natural fair share, and that accumulates, multiplying together each time. So n+2 gives you, roughly speaking, 25%, and you can see then that the difference in weight between something at nice level 0, 1024 in this example, compared to a nice level 19, which is 15, if you have two compute intensive tasks, one at nice 0, one at nice 19, then the nice 19 is going to be very severely disfavored. It's getting about 1.5% of the CPU. So it's just nice to understand. Oh, it's useful to understand how nice it is. I mean, my own major uses of nice are I do stick compute intensive tasks that I don't want to interfere with my other work down at very low nice levels, knowing that when the CPU is quiet, they will get a fair share of the CPU because they're only competing with each other. When I want to do something interactive, like wait for an interactive kernel or build cycle, they will have minimal impact on the system. The degree of CPU they get, the fair slice they get is so small that it's not going to make a big difference to my interactive use of the system. And that's all I need to say on CFS. Like I say, the maths and some of the algorithms are quite interesting, but the fundamental properties you can presumably see after you've seen the way v runtime accumulates. You can see that if something is asleep a lot of the time, wakes up, it will be close to the most important thing on the system, and therefore it will not have to wait very long to go on the CPU. Something that stays a lot of time on the CPU when it competes will make way for other things, is perhaps another way to think about it. So the real-time scheduler. The real-time scheduler is very much that literal set of linked lists that we had up before, except that there is a linked list for each priority level. Just a quick warning, incidentally, in the same way that you've got shed other and shed normal, the kernel has an inverted view of priorities. So outside of the kernel, 99 is the highest priority activity. Within the kernel, I believe 1 is the highest priority activity, and everything gets switched around as it goes in and out of the interfaces. I have never found out or looked indeed why that is, but if you are looking at scheduler code, it is worth being aware of it. And we've got our two scheduling policies, sched-FIFO, sched-RR, and the default time slice that you get with sched-RR is 100 milliseconds. I think we mentioned last week, the round robin is based on the tick config hertz. So you can set this to 10 milliseconds, you can set it to 1 millisecond. If you set it to 1 millisecond, you won't actually get that unless you've got a config hertz equals 1000 system, because the tick won't happen frequently enough. Like I say, real-time schedulers really are very, very, very simple from a computer science point of view. They are just a collection of linked lists and a bitmap to tell you which linked lists are empty as an optimization over the top. So in other words, you can search the bitmap, find the highest priority queue with something runnable in it, and dequeue it and execute it. So it's a super simple thing. It is actually still 01 as it happens. At the point of dispatch, queuing is more expensive, but the point of dispatch, it's 01. And that's all we need. That allows the highest priority task in the system to run whatever's going on. So if you want to visualize it, you've got your bitmap to summarize things, and you've got your queue of linked lists, where you've got null, there's nothing to do. Where you've got actions in it, you can act on them. We have shown you something that is possible, which is a FIFO and round robin task sharing the same queue. That would be a very bad sign, of course, because the round robin would make way for the FIFO tasks, but the FIFO task would not make way for the shared round robin task. So it's not the presence of round robin that causes time slicing. It is actually specifically being a round robin task on the CPU. So the round robin task here will actually be disfavored against the FIFO tasks, which can hold the CPU for as long as they like. And like I said, there's not much you can say about SHED-RT. The algorithms are very, very simple. Deadline scheduler sounded very complicated when I introduced it last week, because we've got to, there's a user, we've got to specify the period, the runtime, the deadline, and other properties of the scheduler. Likewise, we do have to do a little bit of work when we get a tick to find out if we've passed a deadline that it's got to use. So there is some additional back-end activity while the task is running. We occasionally have to check to see if we've got to yank it off the CPU because it's past its deadline. But other than that, it's a very, very simple scheduler. It's also a red-black tree to give us efficient insertion and removal of tasks and the capacity to sort. So the major difference between deadline and CFS is the sort criteria. Instead of sorting on vRuntime, we sort by the earliest deadline. And that makes it possible to schedule certain patterns that you can't actually correctly schedule using a prioritized scheduler. This scheduler is useful for anything that's time-based. So anything that's got a time-based heartbeat is suitable for the deadline scheduler, providing it is the most important thing the system's got to do, because the deadline scheduler sits above the entire of the real-time scheduler. So this is a diagram to help kind of see what's going on and how you get this idea that there can be activities that you want to schedule that you cannot do with a real-time scheduler. And it does involve an example workload, which is of course constructed, so it's not schedulable with a real-time scheduler. So we have 3 tasks, each of which is more expensive than the last. So T1 requires, let's say, 1 millisecond of runtime to execute and complete its activity. T2 is 2 milliseconds, T3 is 3 milliseconds. They're periodic signals, 4, 6, and 8. And the deadlines are the same as the period for convenience. So task 1 has a 4 millisecond window, and it must be executed somewhere within that 4 millisecond window. And then you start a new window, and it must be executed somewhere within the 4 millisecond window again. So T2, 2 milliseconds and 6 milliseconds, and then 3 milliseconds and 8 milliseconds. So T1, you can see it coming up on a real-time scheduler in the bottom left, and it's set as the highest priority task in the system because it has the shortest period. And you can see that it gets this completely square and reliable. Every time it's called upon to run, it runs immediately. Every time it's made runnable, it runs for a millisecond and then sleeps the remaining 3, and it gets this lovely, consistent, clean pattern. T2 has to work with what's left, so it becomes due, all become due at the same time at the dawn of time, and it is then still schedulable. So this one has to wait for T1 to complete, execute, finds the CPU idle the next time, again then it collides with T1, has to wait for it to execute, and that creates the next pattern. The problem is for T3. So T3 had a deadline 8 milliseconds in the future, and it was required to get 3 milliseconds of work in, and in its window it's only actually able to get 2 milliseconds of work done because it's the least priority task in the system. The deadline scheduler will act differently. What happens with the deadline scheduler is there's no longer any concept of priority. When the tasks first come up, T1's deadline is here, T2's deadline is here, T3's deadline is here. They were all made runnable simultaneously, so their order is going to be, at this stage, based on this deadline, T1, followed by T2, followed by T3. What changes is that when T1 is made executable, it actually has the same wake-up time as T3, and it just happens to enqueue at the back because it's the last one to be made runnable. And that results in T3 getting all the compute time that it requires. Because by the time we get to T2, its deadline is right the way over here. So even if the deadline scheduler didn't schedule T3, it happened to schedule T1 in this slot, there'd still be time to schedule T3 before the deadline and before we have to think about when we're going to schedule this particular task. And that will follow up through. Like I say, I'll let you study the rest of the diagram at your leisure. But in all cases, when you have instances, you're looking forward through the graph for the next deadline. So at this instance here, the deadlines are this one, and this one. But this one's already been completed. So this one runs and this one runs because those are in different positions. You can track that all the way up. And that is essentially a schedulable form where the left on a single CPU system, I should add, is not schedulable. The special schedulers, like I said, we don't have to spend too long on these. The stop scheduler is there largely for CPU unplug, and you'll see it as a migration. Oh, sorry, it's not just start unplug, it's also for taking tasks and rebalancing them. So if you've made a balancing decision, then getting the unwanted tasks off your CPU onto the task where you want them, so clearing out the junk from your unqueue essentially, is also a critical activity. And then sched class idle, this happens to have the name swapper, I believe for historical reasons. And it's what happens when there's nothing else going on. So it will do either CPU idle, hot unplug, things like that. So that was the quick tour of the schedulers. Just going to introduce some different ways of thinking about latency, because as we walk through the different preemption modes, this is where we introduce preempt RT, it's important to think about what preemption can help us solve and what it can't. So we have latency. We're looking at the latency to executing this T1 here, this green block. Latency is the amount of time between when a task is theoretically runnable. This does not mean made runnable and put on the run queues. It means the event that is going to eventually make it runnable has already happened. So it's not to the point at which the CPU makes a task runnable. It's the point at which the CPU is on a irrevocable course to make it runnable, essentially. So in other words, the point at which the interrupt fires, if it's an interrupt-driven activity, the point in time where we reach the time, if it's not interrupt-based. So there's a number of things that can happen after an interrupt comes in. The first is possibly that we have to wake up the CPU from a low power state of some sort. This could be a cheap activity if the only power conservation we've done is execute a WFI instruction. It could be a relatively expensive activity if the CPU is actually being depowered for some reason. So wake up latency is important to think about, if only because we might have to limit the power conserving mechanisms to avoid having problems with excessive wake up times. So once we've woken up the CPU, there then may be a latency because interrupts are masked. So we've moved on from the hardware machinery needed to wake up the CPU. We're now waiting to unmask interrupts. Once interrupts are unmasked, at that point, we will execute the interrupt handler and potentially wake up task one. So that's the point at which the task becomes runnable in the sense of the CPU. That's the point at which the software knows that the task is runnable. So here's where it's become theoretically runnable. This is the point at which the task is made runnable from a scheduling point of view. There is then actually some cost to make a scheduling decision, potentially because we have avoided preemption. So if we have got preemption disabled for various reasons, there is a delay before which we can't actually make scheduling decisions. And once we can make scheduling decisions, the next set of latency is what we've called application latency here. This is latency that occurs because something else is running. There is something more important on the system, which is all very well and good, but it still means T1 observes latency before it can execute, which we have to factor into designs. And then finally, if T1 actually blocks and waits for something, there may be some priority inversion latency if we have not managed our locks correctly. So these are different things that contribute to latency. And the things that are tackled by preemption are typically scheduling latency. By having different preemption models, we can reduce the scheduling latency. And by introducing preempt RT as the model, that also makes steps to reduce the interrupt latency for tasks that are appropriately prioritized relative to interrupts, which we'll talk about when we get to preempt RT. And of course, I've just spoken to every slide that's coming up next. I apologize for that. I should have done this one by one. So I've just described wake-up latency to you. One thing to observe, however, wake-up latency isn't purely necessarily software. Purely hardware. On a system using TFA, for example, to implement the low power mode, the time we spend executing TFA to bring power back on and set everything back up again is part of the wake-up latency from the point of view of the kernel. So when we're relying on supervisor level software like trusted firmware, then the time it spends executing, you can kind of view as no different to hardware latency from the kernel's point of view. So we do include certain pieces of software here that may be taking action, but not within the scope of the kernel. Interrupt latency, I hope is kind of well known to people. The behavior of standard Linux is that interrupts are not prioritized. The Linux model is that interrupts run in unknown order. The reality is that different Linux implementations act differently. ARM implementations are typically built along the GIC, and the GIC, if it has competing interrupts of the same priority, will execute the one whose SGI number is the least. So there is actually an imposed order, but designing systems based on knowing that is going to be uncomfortable. So in general, you have to design the system so there is time to handle all the interrupts. The other major contributor to interrupt latency, as well as other interrupt handlers, is periods of time with interrupts disabled, spin locks and things like that. The final one that is slightly less well known is that during interrupt handling, nothing is going to happen to boost the CPU frequency. So if your interrupt triggers while you're running at a very low speed, 200 megahertz, something like that, nothing is going to come in and make the CPU run faster, because the time spent at interrupt is not measured by anything that has control over that sort of thing. The scheduler gets to choose the CPU freak ultimately in modern systems, and interrupts happen behind its back. So low CPU freaks also can contribute simply to the execution time of interrupt handlers. Like I say, scheduling latency is based on a mix of when preemption is disabled and how long it takes to actually run the scheduling algorithm. And application latency is simply waiting for higher priority tasks to get out of our way. Priority inversion we've come across multiple times, and if you have that medium priority task that's blocking a low priority task from releasing a lock, then the high priority task that's waiting will experience additional latency. So the key things we hope to benefit from by changing the preemption model in the kernel is scheduling latency and interrupt latency, depending on which ones we're changing. And for the first three of these first three, preemption for user space, voluntary preemption, full preemption, sorry, we've changed those terminology slightly. I should have fixed the slides, fixed the outline. Those first three are only going to affect the scheduler latency. Preempt RT takes steps to also impact the interrupt latency. So preemption is a way of thinking about how threads are prevented or stopped from executing on the CPU. So it's technically a verb, and it's the act of suspending an executing task in order to perform alternative work. Classically, that is a higher priority runtime, real-time task being made runnable and preempting a lower priority task. Similarly, when a CFS task is made runnable and it has a low V runtime, it can preempt other tasks on the system. Technically speaking, an interrupt is also a form of preemption. Interrupt is something that preempts the running task to run the interrupt handler. But it's a sufficiently important and common use space that we use the term interrupting usually to describe interrupts. So when we talk about preemption in the rest of this talk, it does not include taking interrupts. That's a separate activity. Preemption is the scheduler deciding to allow a different task to run. There is the alternative way of having voluntary preemption, which is essentially voluntary descheduling. You're saying that I need to stop working on the CPU. So if you go to sleep, that isn't preemption as such, that's you going to sleep. But there can also be various forms of voluntary descheduling, such as calling sched yield, which again doesn't cause preemption except among things of the same priority. So they're separate concepts. You've got preemption, which is forcefully taking something off the CPU to suspend it, and voluntary descheduling, which is going to sleep. It's worth noting multitasking can in principle rely on either of these concepts. There is this thing called cooperative multitasking, where preemption can't happen, where every type of descheduling is voluntary. It is still occasionally used on microcontrollers where it reduces the operating system cost enormously. It was, of course, famously used in very early went out of fashion about the mid-90s with Windows 95 being introduced the first time, preemptive scheduling. So it was used on desktops way back in the end of the last century. But preemptive multitasking has become the dominant form because it's more robust and it doesn't require cooperation from somebody who's going to voluntarily deschedule. So preemptive scheduling on Linux, there are essentially four models if we disregard the newest dynamic type. We don't talk about dynamic much in this presentation, so if I've mentioned it, I'll follow through on that. Currently, in all the kernels that you have to pick one of these models. There is a move afoot to introduce something called dynamic preemption model, which allows distributions to ship a single binary and allow the user to select between any of the first three, I think. So you can have a kernel command line that pushes you into a particular preemption mode. Dynamic has some costs, and it doesn't actually change what we're going to talk about. It's still the four models here are the four models. Dynamic is simply a mode that allows you to switch models at runtime, which is not currently possible, but is coming soon. So the four models. after the reminder that user space always supports preemptive scheduling. User space can be preempted at any time. There is always preemptive scheduling in Linux. It's just that in some modes, it only affects user space code. And that's this first case. There's no forced preemption of kernel code. This is dubbed as server mode in kconfig because it trades bandwidth for latency. It gives you enormous bandwidth, which is often what you want on a server. But in exchange for that, you don't get low latency access to particular tasks to run. In future, as we go through, no forced preemption is the terminology used in the kconfig files. For the rest of the talk, I tend to call this preemption only for user space because it reminds you that user space is still preemptible. The next mode is voluntary preemption. Voluntary preemption is similar to voluntary descheduling. It's basically having particular points in the code where the code says it's okay to preempt me now. When you're running in kernel, you hit one of these preemption points, and at that point, we could try and run higher priority tasks. This is dubbed desktop mode in the Linux kernel, and it is what most distributions ship by default. So certainly, I think every machine I've ever delivered this talk on has been configured with voluntary kernel preemption. You then have a mode called preemptible kernel, which is dubbed low latency desktop mode by the kconfig file. That introduces essentially preemption at any point when preemption is not disabled. And preemption is typically disabled when you own a spin lock. So in other words, if you are running in kernel code, but you do not own any locks, you can be preempted at any time. So that's where you introduce the same kind of preemption model you have in most other operating systems to the kernel as well. And then finally, there's fully preemptible kernel, which is preempt-RT. And in this mode, there has been substantial engineering done to reduce the critical sections where the kernel cannot be preempted. So this can massively drop the scheduling latency, particularly because the points at which we have to enter critical sections that forbid preemption have been shrunk down to the lowest possible, well, roughly speaking, the lowest code base possible in exchange for some costs in terms of tracking all the state. And there is increased cost as you head down this list. So maintaining all the state to implement a fully preemptible kernel is more expensive than maintaining the state for number one. So it's not simply that we're costing cache behavior here. So obviously no forced preemption is very good for cache utilization because we don't switch stacks as often, and the refilling of a stack is an expensive operation. But in exchange for that, we have to track, the other benefit we get from that is also we have to track less state, which means the actual state work becomes cheaper. Motivation for this. This is an interesting slide. It dates back a very, very long time to the kind of early history of preemption. And it was asking one of the things that inhibited Linux adoption back in the sort of 2004 window. And at that time, obviously, things like GPL licensing issue, big companies weren't comfortable with GPL at that point in time, which has been mitigated over time. There were bits of the doubt FUD and so on about quality of support, quality of implementation, and so on. But the biggest thing that was holding people back at that point were real time. It was assumed that the real time market the embedded market required substantial real time components. So the limitations of Linux with respect to real time were real and significant. And it's interesting because that kind of survey giving that kind of feedback also matches into the history of things like the preempt kernel 2.4 here and the preempt-RT patch set appearing for the first time. So while people were concerned about it, moves were already afoot to address it. So in terms of preemption evolution, this is the different modes that are available and what's been happening over the years. So the original kernel obviously was built around a classic Unixy concept of no preemption in the kernel code. As simple as that. There was no preemption, and it was uniprocessor. So once you started making your system call, you had the CPU to yourself until you either voluntarily sleeped, just system calls can cause you to sleep. But if you didn't sleep, then you own the CPU until you finished your system call, no matter what you were doing. Fork being particularly notable because it's an expensive thing that clones a lot of data structures in the kernel. SMP arrived in the kernel 2.x era. This still didn't support any kind of preemption in kernel code, and it introduced the big kernel lock for the first time. So the big kernel lock was essentially a giant spin lock that meant that no two CPUs could be executing kernel code simultaneously. It made it much, much easier to add SMP to the system. It had some significant performance problems because you couldn't have two simultaneous system calls. But it made it possible to introduce SMP relatively cheaply to Linux. And the usual folklore that's described about this is as soon as the big kernel lock was added, people started trying to remove it. And that took many, many years to do. So SMP in the 2.2 and 2.4 era, there was still no preemption, but spin locks were starting to become finer grained. The big kernel lock was still with us, but the spin locks themselves were covering more and more of the design space. And during that time, there were kind of lots of experiments with different preemptible kernel trees, usually out of tree, which allowed preemptive activities to happen. Those kind of experiments in the development branch and other things eventually yielded during the kernel 2.6 era the capacity to have different, which did allow it to adopt different use cases. Kernel preemption was particularly popular for pro-level audio manipulation because it allowed you to drive the latencies of audio capture to audio playback very, very low. At this point, the big kernel lock was made preemptible, which means, roughly speaking, it was replaced from being a giant spin lock to being a giant sleeping mutex. The nature of spin locks is because they busy wait. If you preempt and you then compete for the spin lock on the same CPU, you deadlock. There's nothing you can do about it. So when you own a spin lock, you can't be preempted for that reason. So the preemptible BKL was not as simple as a mutex. It was a tremendously complicated lock. I believe it was essentially a form of augmented spin lock into which mutex has been overlaid for local competition, and you automatically released ownership of the lock when you slept. So just describing what it was is a bit of a horror, but it did allow more preemption in more of the kernel. This is also the era where the O1 scheduler was being experimented with. At that point, so this was a long time back, this was about 2003, 2004, I think. There was also all this work to look at preemption and so on. So preempt RT patch set came about and was used for many years against the 2.6 kernel. It makes changes that we will look at in a moment, but in particular, lots and lots of critical sections became preemptible that were not before. The interrupt subsystem introduced prioritization and preemption into IRQ handling, and many of the locks provided priority inheritance to prevent priority inversion. And simply because it's necessary for useful RT activities, things like high resolution timers were added to give us higher precision sleeping. Also things like ftrace were developed, which isn't on this list, but ftrace was also developed as part of this preempt work to help debug it. We then move on into the kind of 3, 4, and 5 major numbers, during which time, you know, the BKL was finally removed. It was actually removed at the very last kernel in the 2.6 era, but that's a detail. Yeah, BKL was removed for the 3 series. And during that time, many of the preempt RT features started to trickle out of the preempt RT kernel and be merged into the main kernel because it made the main kernel better, even for people that did not require real-time behavior. So high resolution timers are generally useful. Threaded interrupts were particularly useful. You know, anybody who's written an I2C interrupt handler and has been pleased that they can use the GPIO API from within it has benefited from the fact that we've got threaded interrupt handlers, because most of the GPIO features can sleep. So threaded interrupts are very useful for particularly low speed interrupts like I2C. But throughout this period, the major invasive hooks, the core of preempt RT, was being maintained separately. So 5.15 was one of the major trigger points. It's also one of the reasons that I thought now was the time to present this course to everybody. I mean, we had this course on the shelf for a year or so before we've delivered it to members. But this 5.15 has triggered a much more significant interest in Preempt RT, because as it goes mainline, people are going to be expected to support it as opposed to having to think about whether they want to. We're not quite at the point where you have Preempt R2 by default. So all the major code to implement kernel critical sections being preemptible, the IRQ subsystem and so on, have been merged, but currently they are not activated. There is a special config option, config arch supports RT, which basically says that you have fixed most of the bugs in particular your IRQ chip handler. And at the moment, no architecture has felt able to set that. So there are still now a few driver fixes that need to be done. And they can be quite minor, and it's well known how to do them. But as that happens, we'll eventually see probably x86 and some of the ARM architectures will lead the way in turning this option on. And at that point, Preempt RT will be mainlined. So we're in this slightly strange point when I'm giving you the talk now. So this talk, anybody who sees it with 5.16 is the current released kernel. I don't think that introduced any significant changes over 5.15. So 5.15, we've seen all the preempt code land, but it's not yet activated. So we'll now go through what it really means to have each of these different preemption models. So preemption only for user space basically means when you make a system call, you own that CPU until the system call exits, or you sleep. In the kconfig language, this is called config preempt non. And it basically means that the scheduling decision happens when you return from user space. So when a task is made runnable, there is actually a little flag. Oh, if you make a higher priority task runnable, there is a little flag that gets set to say, when you are asked to make a scheduling decision, you have to go and look hard because something new's happened. That flag is an optimization. And that flag and the scheduling decision is then made when you return from a system call. So when you return from a system call, we say, do I have to think about switching context? If I have to think about switching context, we go and look at the run queues and pick the next task off. That can result in very long scheduling latencies. As I mentioned, fork is notorious, or was notorious, because it used to have significant locking, and it is quite an expensive operation because it's cloning the entire memory set. While read-only memory is simply referenced, read-write memory has to be handled quite specially. As you might imagine, it's not as simple as we simply copy all the read-write memory. What I think we do in most cases is the read-write memory is marked read-only temporarily, and then when either of the processes touches that memory, that page gets copied and made writable to both of the processes that might use it. So again, it's doing a lazy approach to memory management, just as we saw last week with the memory allocation. Fork can also lazily copy read-write memory by using the MMU to help us. But it's still an expensive operation to work through the virtual address space if it's a large virtual address space and change the properties of every page. So what we see here is these kind of green things, and the process that's being run here is heavily kernel centric. Wherever it's running at the moment, it's making a lot of system calls and they're quite long running. So the period at which we're preemption is quite small. So the places where we could be preemptive are narrow, and these big red sections are scheduling latency. So they are periods where if a new task becomes runnable, we can't put it on this CPU. Voluntary preemption involves a really, really neat bit of insight. So before voluntary preemption was added, there was a debug feature. The debug feature is, you probably know it as config debug atomic sleep, or sleeping while atomic. It's what checks that you do not sleep while you're owning spin locks. And that relies on a debug annotation called might sleep. So all the code paths where sleeping is possible, taking a mutex, taking a semaphore, etc., etc. All the code paths where we might sleep on a kernel object have this might sleep annotation. And might sleep internally says, do I own any spin locks or any other locks that I can't sleep while holding it? And if I don't, then I won't trigger a debug warning. Or putting it another way, everywhere in the kernel where we don't own locks and it is safe to preempt, make a function call to a magic function called might sleep. So if we want to make the kernel more reactive, more capable of preemption, in other words, reducing scheduling latency, what we can do is every time we call might sleep on a not debug kernel, we can just say, all right, well, we don't own any locks. We are safe to preempt at this point. We're exploiting the knowledge that we might go to sleep to say we do not own any locks that prevent us from preempting. So we don't have to be tracking for this. This is the key thing, is because we're relying on annotations, and we can be confident the annotations are correct because we've got lots of debug code to prove that they're correct. With these annotations, we know it is safe to preempt at those points because we do not own any locks. It's going to be safe. So whenever you call might sleep, the kernel will look, check the flag to see if it needs to reschedule. And if it needs to reschedule, it will make a scheduling decision and swap out the current process. So this creates additional green blocks in the big red space. And this is traditionally regarded as a good compromise for kind of desktop and laptop systems. It's enough that when I move my mouse, I can be reasonably confident that the pointer is going to move smoothly whenever however busy my CPU is, no matter what I'm compiling, doing many system calls to the file, many system calls to the file system to grab new header files and new bits of source code. Whatever I'm doing with that, it's unlikely to interfere with the smoothness of my mouse. Now, to be fair, there are also quite a lot of clever algorithms behind, it's called ballistic mouse movement, to try and conceal any remaining bits of latency. So there are some tricks in the display system to make the mouse feel as good as it possibly can. But overall, voluntary preemption is good for making things like the mouse comfortable and work well. And I think I've beaten this horse enough now, but because might sleep doesn't involve any counters, it remains fairly performant. We still have extra preemption points, which means we'll get to have to refill the caches related to the stacks and things like that slightly more frequently if there was some higher priority work to do, but in exchange for that, we do the higher priority work earlier. And the spin locks remain roughly the same cost because we're relying on debug annotation. The spin lock implementation between stage 1 and stage 2 is identical. There's no change to that, which means that bit stays nice and performant. The next level of interactivity tends to be called the preemptible kernel. And during the preemptible kernel, config preempt, it's known as in kconfig, we now have implicit preemption in the kernel, which is the same idea as we have in user space. That in general, we expect the kernel to be preemptible. The only time we can't preempt the kernel is when there's a counter here, which counts how often you've called preempt disable. And when you call preempt disable, the counter goes up. And at that point, we will not be preemptible until the count returns to 0. And at the point we set the preempt count to 0, there is a scheduling decision point at that moment. So when a task is made runnable, there is a scheduling decision point unless preempt is non-zero. And if there is a task made runnable with the preempt count non-zero, then as soon as it becomes 0, there then becomes a new scheduling decision point. So the effect of that now is that almost all the time spent in system calls is preemptible, except when we own spin locks. And that's absolutely fine when spin locks are very small, focused, and narrow. But if you have larger spin locks for, say, page tables or other parts of the system, we still can have relatively wide bars of red in this space. So like I said, this is usually billed as being for low latency desktop use cases. Audio workstations would almost always be configured like this, alongside other things where latency matters, but we're not down to very kind of fine-grained control. You know, even at the fastest level, audio deadlines are in the order of small numbers of milliseconds. Of course, it's expensive if you miss your deadline because your band has just done its best ever performance and you've now got a glitch in the middle of the recording of their most successful performance they've done in a day of studio time. So these are not real time as in life is at risk, but there is a dollar value associated with missing deadlines. The final option is the fully preemptible kernel, preempt RT. And here, the main aim is to reduce to the absolute minimum the kernel code that cannot be preempted. And for the first time, this dives into not just changing the way the kernel works in terms of the spin locks and preemption. It also fundamentally changes the way interrupt handlers work to allow them to be both prioritized and scheduled. With the preempt kernel, interrupt handlers become schedulable entities. They just become tasks that run on the CPU like anything else, which means you can prioritize your interrupts such that some tasks can be more important than some interrupts. That audio workstation is able to have the things that refill audio buffers, even if their DSP that is not run from an interrupt handler, can be higher priority than servicing the network interrupt, for example. So all work is managed by the scheduler. That also means that we can apply scheduler fairness, and it means we can use sleeping locks. And that is the key instrument, but we'll go and dig a bit deeper. But by switching to sleeping locks, we no longer have to we don't have to prevent preemption. When you own a spin lock, you have to disable preemption because competition for the spin lock from the same CPU is a deadlock. Once we switched to scheduler-based locks or sleeping locks, then we now have, when we compete for a lock on two tasks running on the same CPU, we can simply make one of the tasks not runnable until the other releases the lock. So that massively reduces the needs to the blunt instruments that that affect both interrupt latency and scheduling latency. We don't need to interrupt lock nearly as frequently, and we don't need to preempt, disable, and enable nearly as frequently. And that is the fundamental thing that allows us to drive down latencies by having this fully preemptible kernel. So this one we have to dive into deeper. We have to understand each of these techniques that it uses. So the first technique that it brings in is threaded interrupts. And as I've hinted at before, threaded interrupts are one of those things that was moved from the real-time kernel and upstream long before preempt RT was a thing. So we're now 2022. So 11 years ago, this technology was moved out of the real-time patches and into the kernel. And like I say, it had some significant benefits for the mainline kernel. So I just noticed we've got some questions. It's a question about power management and the use of threaded IQs in relation to power management. I'm going to come back to that because power management has some unique challenges related to real time, and there are some slides where I'm going to talk about it a little bit. So I will come back to that when we get there. So our threaded IRQs, they are generally useful, and they work by splitting up an interrupt handler into two pieces. You have a piece which you often call the quick check handler, whose job is to verify that the interrupt we're targeting has in fact been raised, so we can give the correct return code to the IRQ subsystem, and then do something to mask it. It doesn't matter what we do to mask it, it's simply enough to cause the interrupt flag to be lowered. Once you've lowered the interrupt flag, we can then schedule a K-thread, which will run the second half of the handler that does most of the actual work. It's not entirely dissimilar to IRQs and tasklets, but it's not quite as unpleasant. Tasklets, again, we'll talk about a little bit in the future. And it's very similar to concepts. You know what a tasklet is. It's very similar in concept, except that we don't have all the really unpleasant characteristics of tasklets, which I shall talk about later. Once you have most of the work being done from a K-thread, you can prioritize it. You can apply real-time priorities. You can put on the real-time scheduler. You can put it on the deadline scheduler. You can move it where you want it to. And balance its priorities against other activities within the system. The key reason it's beneficial to the kernel is it allows us to perform sleeping waits. And as I mentioned, I2C is a really good example of a subsystem where you really want to do sleeping waits if you have to work with these things. If you're going to use I2C for an interrupt handler, yeah, you want to wait for the I2C controller to do its thing. You don't want to spin lock while you're doing it. And additionally, if you have a threaded interrupt, most of the complexity of locking between the interrupt handler and the other tasks that interfere with the hardware becomes much simpler, because again, you spin lock IRQ save, spin lock IRQ. You don't have to think about which of the APIs you use, because we can use one lock and one language to lock between the two. What happens in preempt RT, however, is slightly more than this. Everything I've described is this threaded IRQs in the mainline kernel. What happens with preempt RT is that almost all interrupts are forcefully converted into threaded IRQs for us, regardless of whether there have been any code changes and regardless of whether they attempt to use threaded IRQs. Almost all interrupts are forced to become threaded IRQs. And that works because on architectures that support preempt RT, you can synthesize a quick check handler for all interrupts without having to have code for it, which roughly translates into they come up, they look at the GIC interrupt line, and then they mask it at the GIC. So you don't need to do anything about the peripheral to stop the thing from interrupting this. There are some types of interrupts that cannot be converted to threaded IRQs. So no thread, things like timer interrupts, interprocessor interrupts, some of the perf CPU stuff and one-shot do not get converted. But the vast majority of normal interrupts will do that. So representing this graphically, classic interrupt handling with a single interrupt handler that runs from interrupt is basically you have a task on the system, interrupt fires, we execute the handler, we return. Threaded IRQ handling. Firstly, we're going to spawn off a K thread. The K thread will have a set of default properties. As it happens, the default properties for thread functions is to run as shed FIFO tasks with a priority of 50. So they will preempt most activity on the system, but you can construct real-time tasks that sit at a higher default priority. You can also reach in with some of the APIs that we discussed last week to change the priority of the thread function. So you can either boost the priority, you can switch it to deadline, whatever it is that you need to do. The default is shed FIFO 50, but you can change that, which allows you to prioritize which interrupts happen before others and things like that. In the kernel API, this is providing a handler and a thread function. So the quick check handler will run at interrupt, and it will then cause and make runnable the thread function. And in this case, we have a higher priority task that runs ahead of the thread function. And eventually, when this either sleeps or when it sleeps, the thread function can run. Like I said, the normal case on a system that doesn't have any real-time components, of course, is that the thread function runs immediately because there isn't a high priority task competing with it. What is happening with preempt RT is that we are forcing interrupt threading. And even this is actually mostly mainlined at this stage. You can force this on a standard kernel. What is happening now is a implicit quick check handler is created by the architecture essentially to run at interrupt level. So the handler that you provide to request IRQ is not run at this point, nor is the quick check handler you provide to the request threaded IRQ. What happens here is we have a architecture supplied interrupt handler, which will vary depending on your IRQ chip, but think of it from a GIC point of view as being you check the GIC source and you mask at the GIC. It will actually mask at your leaf IRQ chip. If you've got a cascade of GIC and then a couple of IRQ chips handling other aspects of your SOC, it will reach to particular IRQ chips and mask the individual line. But yeah, if you haven't got particular IRQ chips on your system or you're unfamiliar with it, it's just reaching into an interrupt controller and masking the interrupt to the interrupt controller. That then allows us to drop down to normal scheduling. We can run the user supplied interrupt handler and the user supplied thread function if there is one. And at that point, after we've completed the handler here, again, a piece of implicit code can re-enable the interrupt and make it serviceable again. And then we move into the thread function. I beg your pardon, that's wrong. Thread functions when you re-enable it, but yeah. So that is forced RQ handling. And it creates other concerns, shall we say. So the next thing we want to do in preempt-RT is we want to eliminate spin locks, because spin locks prevent preemption, and the goal of preempt-RT is to make as much of the kernel as possible preemptible. So the way we can achieve that goal is by making spin-locked sections preemptible, which cannot be done if spin locks are spin locks, because the nature of spin locks is they cannot be preempted. And what we can do is we could take that spin lock API that we have in the kernel and implement it using a sleeping lock. If we implement it using a sleeping lock, then we gain the capacity to take those locks from interrupt safely. So let me try. Where are we going here? Sorry, I'm speaking to one aspect, and the diagram is actually describing a different concept than I'm describing, which might be causing a little bit of challenge for a few people. So the spin lock converted to mutex is showing why we have to have threaded mutex, why threaded mutexes are mandatory. Sorry, why threaded interrupts are mandatory for preempt-RT. So it's showing a situation where we've not got a forced threaded interrupt handler, it's a regular interrupt handler, but we have converted spin locks to mutex. So the reason we converted spin lock to mutex is to make the kernel more preemptible. The problem we have with that is that so this is a motivation for the sleeping lock. This is a spin. Double check where I'm going on this. I'm describing cause and effect in different ways around, and it doesn't really matter which one is cause and which one effect is, because they're both fundamental to reducing the costs of the latencies involved in preempt-RT. But this is showing what's happening if you've got a spin lock. So if this is a threaded IRQ and we're taking a spin lock and we're allowing preemption, then the threaded IRQ can overtake us. We take the spin lock and things go wrong. So by replacing it with sleeping mutex, we get a much better approach, which is we have the supplied implicit handler that's coming from the architecture, and we have our real handler. And because they're using mutexes, then the green thread here can take the lock, the handler can run, the handler, the moment it tries to take the sleeping lock, so it's calling the spin lock API, but it is it's actually under the covers using a threaded mutex, sleeping mutex. So at this point, we take the lock, the handler goes to sleep, the original thread runs until it releases the lock, and then the handler can take over again. That's what happens when we have the spin locks converted to mutex. So the benefit they give us is that we can be preemptible for much more of the time, because now we have interrupts that can sleep naturally. We are able to convert those spin locks over into sleeping locks. An additional detail is that the mutexes that the spin locks get converted into are a thing called the RT mutex. So the RT mutex is a mutex that implements the priority inheritance protocol. Again, it has been merged to mainline, and again, it is fundamental to the implementation of existing kernel features, in this case, the futex. The futex is the underlying feature that allows the user space to implement POSIX mutexes. So when we talked about pthread prior inherit last week, what's happening under the covers there is the C library is providing the POSIX implementation that's implemented using a kernel feature called futexes. And in a non-RT kernel, the only significant user of the RT mutex structure is the futex. What happens when you turn on preempt-RT is that RT mutex gets used pervasively. So the spin lock API is switched over to use RT mutex. And that SpinLock API, as we hinted at the last slide, but I didn't yell specifically, is that SpinLock and SpinLock IRQ save have an identical implementation. Because we no longer need to lock interrupts, because we're relying on a sleeping lock, then SpinLock and SpinLock IRQ save are both boiling down under the covers to RT mutex lock instead. Additionally, all the regular mutexes within the system are also converted to RT mutex. So wherever you see a mutex lock, when you're on a preempt RT system, you'll be using a mutex that supports the priority inheritance protocol, and so you cannot get priority inversion problems when you have regular mutexes in your drivers. So it doesn't matter if a system call comes in from a real-time thread and a not real-time thread and an intermediate thread. When people attempt to lock that mutex, you will get priority boosting until the lock is released. These are the same diagrams you saw last week describing priority inheritance. It's mostly a reminder, or if I'm delivering this lecture without the first slides. So it's describing that mechanism of priority boosting to avoid priority inversion. And that will happen for all kernel mutexes, all kernel spinlocks by default if you're using preempt RT. So if you want to use preempt RT, it is not yet fully upstreamed because it hasn't got all the enablement. So although most of the code is in the kernel, there is still a preempt RT patch set. It's still being maintained to 5.15, 5.16, and so on. So you need to go and find those patches and you need to apply them to your kernel source tree. Once you've applied them to your kernel source tree, you're then in a position to enable config preempt RT on the supported architectures, which does include both ARMS and x86. Now, it's fairly obvious at this point that the changes made by preempt RT dramatically impact the dynamic behavior of the system. Whenever you take an interrupt, the code paths are changing enormously, the scheduling processes are changing enormously, the timings are changing enormously. Whenever you take a spin lock, the code paths have been dramatically changed. So some drivers may require changes to work correctly after being force threaded. Some of the low-level drivers might also demonstrate problems because they're not using the correct spin lock API. Now, let me explain what that means. If you've been connecting the dots really fast in your head, then you'll have noticed that I have said, that some interrupts, no thread per CPU and one shot, need to manage the low, cannot be threaded, that these particular low-level types of interrupts cannot be converted to threaded interrupts. So even on a force-threaded system, these interrupts run as regular interrupts. I've also said that sleeping mutexes are incompatible with competing between user space and interrupt, in regular scheduling and interrupt, because they can produce that deadlock that I was not speaking to as accurately as I should have done. So this particular one here, you take a spin lock here, you go into a hardware interrupt handler and take the spin lock again, you will get a deadlock. Until you have converted that handler into something that is schedulable and therefore something that can sleep, you will get a deadlock when you take that spin lock. And that's still true. For all of these things that could not be converted into threaded IRQs, that will still be true. It will be absolutely impossible to use the spin lock functions because they are sleeping locks. Now, this has been known about for a very, very long time. So the kernel introduced a data structure called the raw_spinlock_t for the intent that drivers that know they are using one of these features should be using. And this annotation was introduced in 2010. And so I feel a little bit guilty saying because you're using the wrong SpinLock API, because until now, it's not been enforced. So although the SpinLock API was introduced in 2010 to solve this problem, and the assumption is that anything that no thread per CPU one shot should be using raw SpinLock instead of regular SpinLocks, it was not enforced, it was not well known, it surprises people. But if you have drivers based on this thing, or indeed any IRQ chip driver, which technically doesn't implement these things, but it is providing those first level handlers, that implicit. If you've got an IQ driver, you're running in that implicit interrupt handler that's produced by the architecture. So in all those cases, you have to be using the raw Spinlock API for all your activities, or you will get problems and risk of deadlock. So this hasn't been strongly informed. There will be latent type bugs here. So after you have enabled the patch set, I think the simplest and strongest piece of advice you can have is you should spend a period of time running with config debug atomic sleep, because config debug atomic sleep will catch any of the situations where you've got interrupt handlers like this that are still running as regular hardware interrupts, but they are incorrectly using the Spinlock API. And the fix is as simple as placing raw underscore in front of the APIs that are presenting to you in stack trace. And finding all the other uses of the same Spinlock. But yes, it is a relatively simple transformation. Likewise, if you've ever been curious, if you've ever read Spinlock.h and thought, why does it do Spinlock lock and then use all these wrappers to go straight down to raw Spinlock? This is the reason. The raw Spinlock is there for things that cannot be converted to threaded interrupts in preempt RT systems. So final couple of details that I want to bring out to people. First is a matter of philosophy, and that is that throughput versus responsiveness is always a potential competition. And one of the reasons for having these 4 different modes that I've just been describing to you leading up to the very, very complex implementation of preempt RT is that sometimes we've got to pick a side. We've got to say, are we more interested in responsiveness or more interested in throughput? And the reason for that is mutexes are much more complicated than Spinlocks. They cost more to do. The fundamentals are the same. They're test and set or equivalence, atomic actions. But the action under contention is much more complicated for mutexes. The code paths are enormously long. That's why Spinlocks exist. Spinlocks allow short atomic, short critical sections where the cost of sleeping and waking is more expensive than just spinning. That's why Spinlocks exist. That goes away if you're on preempt RT. Having priority inheritance makes things even more complicated. I've implemented priority inheritance. It is a whole bunch of complicated links between the mutexes on different run queues. Sorry, mutexes and the tasks on the mutex queues. That is all additional state tracking. Maintaining preempt count, which happens at preemptive kernels and fully preemptive kernels, is extra atomic activities on every single Spinlock. Going to threaded IQs increases the interrupt overheads. There are costs to turning on all of these features. And like I say, they're not always in conflict. If they're not in conflict, kernel developers will look for solutions that improve both. And I think the example of preempt dynamic, where dynamic itself has a cost, but it does allow you to select the different models at runtime, is a good example of trying to find ways to do this missed. However, the kernel has a long heritage as a server and desktop operating system. If there is unavoidable conflict, throughput will usually win. And that's not the sky falling in, because a lot of the time the conflict can be avoided, but where there is conflict, throughput usually wins. And the reason it's important to understand this is that helps us understand some of the kernel's decision making, in particular related to soft IQs and tasklets. Soft IQs and tasklets are a fundamental example of some trickery that does improve server bandwidth considerably, and is therefore difficult to remove because it solves some real problems for performance on throughput-oriented systems. So we do need to talk about these a little bit because they do have some peculiar properties. So soft IQs and tasklets are a historical means to defer work from real interrupt handlers. So before we had threaded IQs, we had soft IQs and tasklets. Tasklets, incidentally, is a data structure that sits on top of soft IQs. So soft IQs are basically ways to say, I want you to run a handler. And when you leave interrupt handling, you jump, instead of jumping into the scheduler, you jump into a soft IQ handler instead. So when you leave the hardware IQ state, you don't go back to regular scheduling. You run this extra kind of interrupt-like thing that preempts all other activity on the system and is unknown to the scheduler. Tasklets are simply a data structure on top of that that makes it easy to manage the work that you're going to do. And their goal is to defer work, and it was originally a means to boost interrupt reactiveness by taking a long-running interrupt-related activity and making it lower priority than the rest of the interrupt system. So just as you could have a threaded IRQ that has a short handler and then wakes up a K thread, soft IRQs were a way to have a short handler and then go into this soft IRQ state. Soft IRQs have some seriously odd semantics. First, they can be raised from both normal and IRQ context. If they're raised from IRQ context, they wait until you leave the IRQ state. If they're raised from a normal context, they essentially run immediately and preempt other activity. They are run with interrupt enabled, which is what allows them to reduce interrupt latency to other components. Where they're executed from actually varies. Normally they run at very high priority, blocking all other kernel activity, unless they use too much CPU time. And if they consume too much CPU time, they instead get bumped down to run from a shared other kernel thread called ksoft-irqd. And the decision to make that is based on them running for too long. And the reason for that is actually networking. Networking was one of the original users of soft IRQs, and it allowed you to take complex work happening in network handlers and run it in a soft IRQ so that you could take other IRQs while you were doing it and keep your serial ports happy and things like that. Of course, if you get a network storm coming in, blitzing the system with packets, it is important that it doesn't spend all its time handling packets and it does some useful work instead. Hence, there's this pressure release valve that if you spend too long in these relatively high priority soft IRQs, they suddenly get made low priority until the packet store ends. So they're very, very unpredictable. And from a bandwidth point of view, this isn't actually a bad thing. But from a real-time point of view, having important things that suddenly become unimportant because somebody else has started a network packet storm is just really hard. You can't design real-time systems in the presence of this kind of behavior, or at least you have to assume they're out of scope. The other thing about soft IRQs is the scheduler is completely unaware of them. So you can't sleep from a soft IRQ because the scheduler is unaware of it. And more than that, soft IRQs steal vRuntime. So CFS is doing its best to be fair, but if a process has half of its CPU time stolen by soft IRQs, that's tough. It will still get knocked off the CPU. Likewise, it is consuming the period from your, sorry, the period? Yeah, it's the runtime. It's consuming the runtime from your deadline task. So if your deadline task says, I will always execute within a millisecond, and you spend 95% of a millisecond, 950 microseconds, handling soft IRQs, your deadline is going to get throttled. Likewise, the real-time runtime, if you've got that limit of runtime applied to a real-time process, soft IRQs steal it all in not preempt RT kernels. So, I mean, the usual answer about tasklets is don't use tasklets. Don't use soft IRQs in your drivers. Unless you really want to, which is where it gets interesting. So in general, deferring work from interrupt to tasklets is there to improve latency for other drivers. You can achieve the same goal by switching to threaded IRQs. So if the goal is simply to take a system and not spend too long in the interrupt handler, then threaded IRQs are usually a superior alternative. But throughput wins. And there may be cases where you really do want to race through a piece of work. You want it to happen at highest priority situation in your soft IRQ, which is all very lovely until you hit this takes too long. So soft IRQs are really, really quite peculiar things. They do get better with preempt RT. So there's been an iteration of design, actually. It's one of the most, I suppose, modern changes to preempt RT. A lot of preempt RT, if you read about it, and there was lots of kind of papers and LWN articles back in the 2010 kind of era. This was one of the major things that changed after a lot of that literature was written. So It used to look pretty much like KSoftRQD. You had a thread to handle soft IQs instead of handling them as this special execution context. So it basically got rid of them and turned them into their own thread. It was analogous to hardware IQs, which were converted to their own thread. So each soft IQ bit, there's 7 or 8 different bits for different purposes. One of them is the taslet bit. Each of those was switched to its own thread. And the reason that didn't survive is because it proved very difficult to tune to make the system stable. Because its effect now is that network RX and TX each has its own thread in the soft IQ system. But what priority should you set it to so that during a packet storm, it doesn't dominate the CPU? You either have to set it low, in which case something goes badly wrong, or you have to set it ridiculously high and do some kind of fast path to prevent the network from dominating the system. So it was difficult to tune. And there was also some performance issues associated with it. Soft IQs were introduced to fix throughput problems. And so if you have sluggish scheduling for any reason, they don't do the right thing for you. So the modern version, the current version in Preempt RT is dubbed No More Victims. So the goal here is that all action is happening from something that is schedulable, but that if there is a victim as such, it is the person that raises the soft IQ. So if you are calling and raising a soft IQ from a schedulable context, which does include interrupt handlers that have been force threaded. So if you're running with the schedule, if you call sleeping locks basically, and you raise a soft IQ, then that soft IQ and only that one will be run from your thread as soon as you re-enable soft IQ handling, which in the case of interrupt handlers means finishing the interrupt handler. So now the thread that raised the soft IQ will execute the soft IQ. If you raise a soft IQ from something that's not schedulable, timer IQs, per CPU stuff, and so on, then that will be deferred to KSoftRQ as it was previously. That's still a schedulable entity, but now most of the other things that happen with soft IQ don't interfere and don't get lumped together. So what that means now is that all soft IQs are run from scheduler entities. They don't steal time. If they are taking time, it's because you have asked them to run. And so they can be subjected to any fairness or throttling that is configured for that thread. Approach to soft IQs does. And we do just want to sort of finish up with something about networking. The default configuration, the networking stack, makes very, very heavy use of soft IQs for packet RX and TX. And this is a fundamental feature. In part, it's because you can have quite a lot of packet activity, and in server systems, networking is fundamental, important, and critical. So there's a thing called the new API, which is so new, it's been with us for nearly 20 years, I think. And it is a selection of callbacks that the network stack will normally call from soft IQ context. It is used for both regular networking and, in fact, XDP fastpaths also call from soft IQ context. So XDP is basically a packet filtering system that sits there at the earliest stage it can in network interrupt handling, working out what to do with particular packets, whether to discard them, treat them as normal, or fastpath them down particular avenues. So it allows a kind of hybrid of data plane and regular networking to exist within Linux. They can be triggered from a mixture of sources, both the threaded IQs that are attached directly to the network card, but much more commonly from timers. And because they come from timers, that means they're going to get punted down to KSoftRQD. They're going to be slightly difficult to manage because the whole thing is, whole of networking when it's running from timers is going to get pushed down into this K thread. From a real-time point of view, I just wanted to bring this up as a hazard. And also observe that if networking is outside the scope of your real-time system, so if you remember how we just constructed the example real-time system from last week, I had described it as networking not being in scope. The mesh networking stuff was just shed other, and it was being done. So it has to be observed that if you are running Preempt RT and networking is not part of the real-time system, then we can hope that CFS does a good enough job with that work being hand deferred to ksoftRQD. It is shed other, and when networking is nice and light, when we're just getting a few packets coming in to send us command and control information, then it will not dominate the CPU, and therefore it will sit nice on the left of the tree and will be picked off at relatively high priority, and we should get our network packets with a reasonable latency associated. And similarly, if you get a packet storm, CFS throttling will come in and do something similar to the crazy SoftRQ stuff, that if you overload the SoftRQ system, it switches over to a different execution context. So it's not perfect, but it should be good enough for most systems that where networking is outside of scope. I am not able to talk authoritatively on time-sensitive networking, but when network comes into scope, there's a couple of things going on to do real-time networking. One, from the node's point of view, obviously from the routers and everything else, it gets more complicated. But from the node's point of view, it's having prioritized access to the transmit by having queue disciplines, and it's ultimately by trying to get packet out of the network and into the right place as quickly as possible, where sometimes XDP plays a role because it can filter out real-time activity and punt it down particular queues. However, if it's running from that SoftRQ shed other, we now have to figure out what to do with it, because if real-time has come into, if networking has come within the scope of our real-time system, we are going to have to work out how to correctly schedule all this network RX queue. And so the only advice I can give you really is that you should take a very, very close look at a thing called NAPI threaded mode. And it's basically a sysfs control that you can reach, and it can, at runtime without any problems, dynamically switch you from using SoftRQs as the mechanism by which you realize the deferred actions from the network stack, and instead the network will defer actions to individual K threads. So I believe you get a K thread for TX and a K thread for RX, and possibly even for separate queues. I haven't studied it in detail. And this doesn't solve the whole problem, because you've still got to work out what priority to put these K threads at. You've still got to figure out how to cope with packet storms, although you could put in XDP-based defenses. But you should then be able to have finer grain control. Additionally, of course, if you've got multiple network adapters, it means the real-time one can be separated from a bandwidth-oriented one. So, like I say, I cannot go into enormous detail about this, but to warn that when networking comes into scope, SoftRQs are going to be something you should look at, and the kernel does have mechanisms to mitigate it by switching on NAPI threaded mode. As ever, NAPI threaded mode was not invented for real-time, not as ever. This mechanism has also got benefits that extend beyond preempt RT. So it was actually pushed by companies that were having problems during packet storms of not doing useful work. And by moving this stuff down to shed other, the fairness thing allowed them to balance together the processing of incoming packets versus actually reacting to the incoming packets. And it gave them, by basically allowing CFS to do its job, instead of the SoftRQ heuristic, it gave them a better balance of activity during packet storms to allow useful work to happen alongside the processing of incoming packets. So yes, it was interesting that this particular mode, while it is sort of less efficient, it's using a heavier weight process scheduling of an activity instead of SoftRQ. By allowing the mathematically rigorous CFS to understand the distribution of work during these systems, it actually does in certain systems result in better server behavior as well as being useful for real time. So that's all I wanted to say on the subject of preemption evolution. Preempt RT is definitely a interesting technology, and where you have a specification that you must meet, it can be a good step towards trying to meet it. So this is a quick detour into timers and timekeeping. It's only going to introduce you a couple of pieces of kernel where we keep track of time, to help us understand between a couple of key differences that can be useful to think about, kind of similar to the difference between non-real-time and real-time activity, and the way the Linux kernel and I have been encouraging you to think about them in starkly separate terms, where one, you rely on CFS to give us good heuristics, and for the real-time portion, we rely on either RT or deadline to give us real-time characteristics. There are some analogous things going on with timers, which I think are kind of interesting. So first of all, timers, how do they work? So in the kernel, there is a couple of concepts that are related to time. The first is a clock source. And a clock source is very little more than a hardware abstraction of a free and running counter. And the purpose of that clock source is to provide a timeline that tells you where in time you sit. When you ask for the time of day or the clock monotonic, it tells you what time it is. And the kernel has multiple drivers and multiple different ways, multiple timers that can be attached to the system. And the drivers is register clock sources. If they can provide a clock source, they register a clock source. Alongside the actual implementation of a clock source, it also gives you essentially a quality rating, where there's a strata of things that can only be used for boot up and test. For example, a spinning loop. A spinning loop measured against something that's not useful for measuring time, like the real-time clock. So the real-time clock, if it ticks per second, has very little utility in a computer for telling you the time for most purposes. It obviously tells you the wall time in seconds, but if we care about microseconds, a real-time clock isn't any use. But what you can use a real-time clock for is to find out how long it takes to execute a busy loop. And then that busy loop can be used for short delays and provides you a clock source that is only really suitable for boot up and testing, because the time will only pass while you're spinning. Then you hit up for sort of functional for real use but not desirable. This is things with poor granularities, correct and usable. So this one is now a useful time source, but perhaps is accessed via MMIO registers and isn't very fast. And as we go up, we eventually head towards this ideal clock source. So an ideal clock source is really fast to read. It presumably has minimal jitter and can be accessed possibly identically from multiple CPUs and so on and so forth. It might work very well for S&P as well. And the reason we have a rating is, speaking approximately, the kernel will not use the second best clock source. Why would it use a second best copy of time? It should always be using the ideal best clock source it can get. The reason for the equivocation is that the ideal clock source might have a small drawback, which is that it stops ticking if you unpower the system. If you put the system into a deep sleep state, an ideal clock source can stop ticking, in which case there can be an auxiliary clock source that continues to tick while the system is in very low power states, and then the time is then synced back when we start back up to rework out where we are in natural time with this ideal clock source. But other than that, second best clock sources simply aren't used. And in the case of ARM64 world, the ARM architecture timer is the most commonly used clock source because it is very close to mandatory. In almost all practical designs, it's mandatory because you won't get the certifications you want if you don't have it. And it is fast. It's based on coprocessor registers, so it is very fast to read. It's got very high precisions. It was specified to give us precisions. So it is almost always going to be the best clock source available on ARM64 systems. It's usually the best clock source available on ARM v7 systems as well, although it doesn't have a coprocessor interface on a v7 system. And so we have fairly simple mechanisms to read it from particular registers. We can convert it from its own cycle time to nanoseconds with simple math. And it gets registered as a particular rating with some flags and everything else. And that's how you register a clock source. A quick aside about scheduler clock. There is a function called shed clock, which is used by the scheduler to measure time. And it's a very peculiar clock. Because the scheduler is a really, really hot topath that is very frequently called, It's one of the very few places where the kernel is willing to trade speed of reading a clock versus the accuracy of the clock you get. So shade clock is defined to return this number of nanoseconds since which the system has started. There is a default based on the Jiffy counter, which is very poor granularity. And it's used to measure things like the accumulation of VRuntime and other things. And more than that, it can be called from pretty much any context. So it has to be IRQ safe, NMI safe, and so on and so forth, and still give you a sensible value. On ARM systems, the architecture timer meets the criteria to be a scheduler clock anyway, so it tends to be the same clock. But if you are on other architectures, shed clock can be using a different timekeeping mechanism to gain some of these properties of being tremendously fast. The reason we bring it up partly is because the scheduler clock and the scheduler tick are completely different concepts. So I just wanted to express here that the scheduler clock is a clock source that is used by the scheduler to measure things. The scheduler tick, we'll get to in a moment. Oh, things are out of order here. So this is ARM architecture time just registering itself as a scheduler clock as well. So having said that ARM architecture timer provides a good quality scheduler clock, it does also register the scheduler clock in this case. So again, on ARM v8 systems, then the main clock source and the scheduler clock source will actually be the same timer, but it's not mandatory. The other concept that comes up is that of clock events. Clock events, I suppose, are perhaps the reverse of clock sources. They take a desired time and poke values into hardware timer registers so you get a interrupt or other asynchronous notification that the timer has gone off. So this isn't about orienting us in time, it's about waking us up at a fixed time in the future. On SAP systems, it is ideal and, like I say, customary in the sense that you expect designs to provide this to be a good quality SMP implementation, is to have a clock per core so that you know, if we've got a task that's made runnable at a particular time, we can get ready to do that. We can do sleeping, high precision sleeps and things like that on a per core basis. It saves us having to do interprocessor interrupts unnecessarily. Another use that the clock events are used for is to provide a periodic tick, which is quite often called the scheduler tick. And like I say, it's completely different to the scheduler clock. This is a periodic event that classically runs 100 times a second. So very low resolution, a 10 millisecond tick. That will do a number of things. It will update the Jiffy count. Jiffy count is a low resolution fast clock that is used for various types of timekeeping in the kernel. It will do things like processor counting and time slice expiry. So however fair CFS is, it's only fair once every 10 milliseconds. That's when it checks the V runtime expiry. It doesn't work out when it's going to expire. The tick tells us to check to see if the task underneath us is ready to change. It runs things like load accounting, driving Pelt and helping make decisions like that. And it's also used for certain types of deferred work like read, copy, update, callbacks, and IRQ activities and things like that, IRQ work activities. So it's used for a lot of housekeeping ultimately. The default's 100. It can be changed to 1,000. Although I think I would claim that in most modern systems, the necessity, it was quite common to run embedded systems in the sort of 15 years or so ago, maybe, to boost config hertz to boost interactivity. It shortens the it shortens schedule latency. It increases tick resolution. It increases tick-based wake-up times, things like that. I don't see it used quite as often these days, largely because high-resolution timers have been added, and high-resolution timers provide an alternative way to do wake-ups. And the clock event source is also capable of driving high resolution timers. So in this case, you have on this right-hand column, essentially, we've got a lot of kernel concepts that can be built on top of clock events. So clock events themselves, again, if you're interested in looking at it, have a look at it. It's slightly overcomplicated as a piece of code because, if I remember rightly, it is shared between v7 and v8 implementations, and therefore shared between memory mapped and coprocessor based implementations. So it has a little bit of noise around it, but you should still be able to find interesting things if you go looking. So we're requesting a per CPU IRQ. That should be ringing notifications about use of spin locks and things like that after you talk about preempt RT. That means it's got our interrupt per SMP core that we wanted. So we can set these things up. We've got registration, we've got a rating, how high the quality is, and so on and so forth. So we have, you also notice this is, I think, the same driver that we looked at twice before. It's the same file. So the same file is providing all the concepts because on ARMv8 systems, that single timer is the best implementation of both clock source, clock event, scheduler clock, the whole lot. So you'll see it registering multiple different things. Now, this is where this difference that I want to really push on between high resolution wake-ups and the timer wheel comes into play. So the timer wheel is a timeout and expiry mechanism that hangs off the scheduler tick, meaning it has a relatively low resolution based on the default tick setting. And it's primarily used by networking and device drivers to detect when events didn't happen like we expected to happen. You know, when somebody opens a TCP connection, we expect them to, when we've replied with the what's it, SYN, and ACK. So we've replied with our SYN ACK, and we're expecting our partner to send us an ACK. But if we don't, we have to clear out some state. So when we send our SYN ACK, we also stick something in the timer wheel to say, tell us if we hit this deadline without us starting us up. Timer wheels are viewed as having no particular strict resolution times and no particular real-time deadline. Instead, they are hugely optimized for add and remove, because when you are waiting for a timeout, the default case is the timeout never triggers. If you've got a guard on your SCSI drive, it's usually 5 seconds long, and at the end of 5 seconds, it's going to abandon the SCSI command or send a redrive reset. So that doesn't require, you know, waking up to microsecond precision exactly 5 seconds after we queued this thing. That's an irrelevant level of detail. But you know, my drive responds to SCSI commands for a year without ever timing out. I'm very lucky, but that's what I think it's done. I haven't checked the logs to be sure, but I'm fairly sure my hard disk isn't dying, and therefore it is reacting to all these things. Every time we send a command, we've got this backstop going in, but we want it to be cheap. We want to be able to add and remove timers very, very cheaply. So the basic add timer APIs and Del timer are optimized for add and remove. They're not optimized for wake-up resolution. The timer wheel is in fact based totally on this observation that when you set a timeout, the granularity that you require the timeout to meet for correctness actually varies with the length of the timeout. You know, if you have said, I want to time out after 10 milliseconds, and you throw that onto a queue with a granularity of seconds, then that's not great. However, if you ask for 5 seconds and you get 5.5 seconds, does anybody really care? Not so much, no. So the timer wheel is actually based on this idea that you have multiple levels based on how far the expiry is in the future. These levels are drawn for config hertz equals 1000 as it happens. The granularities and the ranges are subtly different. If you switch this down to 100, I think you just multiply everything by 10. And if it's 250, it does get a little bit more mathy, but not very much. It's a multi-level thing, and it's based on this granularity changing by a factor of 8 each time you go up. The consequence of changing by a factor of 8 is that the worst case, which is, I think, queuing for this queue at this threshold, is a difference of 12%. So if you ask for a 64 millisecond delay on this system, 65 millisecond delay, you'll end up quantized to 8 milliseconds. And that's not too bad. Like I say, the biggest error that's going to arrive at is 12.5%. So that's the timer wheel, and it's based on that observation that timeouts are not usually precise. On the other hand, triggering real-time activity is precise. Waking up, doing something, if we've got to have an event where timing out is the normal case, essentially. So timer wheel is for cases where timeout is the exceptional case and removal before expiry is the normal case. Other uses where we're predicting activity that's going to happen in the future, like those control loops from our example, they don't want to say, just because I'm waiting 10 seconds, I want an imprecise wake up. At least we can't know that. So that's where high resolution timers come in. High resolution timers on systems with really poor quality clocks basically run from jiffies. The jiffies is the backstop. So if you haven't got anything better, then even these APIs will adopt the jiffy clock. But jiffy clock does not have a very high quality rating. So on most systems, you end up with a much better clock event source. And so we have user space APIs that will automatically adopt accurate wake-ups. So we have things like nanosleep, which we introduced last week, POSIX timers, interval timers, all use high-resolution timers, as does peephole and pselect and other things related to waking up with expiry times. So the user space APIs that I introduced you to last week, when talking about real time, were all going to be based on high-resolution timers. Likewise, if you have a driver or subsystem that is going to require precisely timed wake-ups, perhaps multimedia systems that need to go and read a camera off USB to achieve their 25 frames a second, they are best off using the high-resolution time API. So it requires, high-resolution timers tend to be described as having nanosecond resolution. They don't have nanosecond granularity, but the timeouts you request from them are expressed in nanoseconds. So they're immediately queued based on a single list of activation time. They have accurate timer expiry, and ultimately, when the clock event source is being programmed, you basically dequeue from the list all the expired timers, and then whatever one you've reached that has not yet expired, you queue that as the wake up, and that's how you cope with your list of expiry times. There is an API in the kernel. If you do want to use high resolution timers and you aren't implementing that kind of timeout concept, then that's the API you use to do it. Read up on it if you want to write these things, but that's the key reason I've gone into this little segue about timers, is to lead us into the idea of timeouts. We're using the timer API. Events that have to happen at particular times, we use the high res timer API. And the final thing, this is part of the reason I deferred some of the questions about power, or comments, and the comments about power. Power saving is probably the biggest hazard to real-time behavior, other than badly designing in the first place. And that's because both of costs and latencies of entering and exiting low power states, possibly costs and latencies to do with changing CPU frequencies, and simply running with lower performance. If you've got systems where the performance of the system can dynamically change, then you have to design your real-time system to work correctly, either by always working at the minimum CPU frequency, so whatever frequency has been picked, we can run correctly, or by ensuring that if we come under complex loads, we spin up the CPU frequency fast enough to react, which is incredibly hard to do. So usually you end up with a baseline minimum frequency. This is an example of the sort of thing that can happen. So this is a diagram of a CPU going into the lowest power state it can manage on the top line, and then the corresponding wake up when some wake up event happens. So roughly speaking, there is a point at which the CPU irrevocably decides to go to sleep. So it locks out, interrupts, and it starts calling into PSCI to send the system to sleep. So if just at the moment you disable interrupts, an interrupt, it doesn't have to be a timer interrupt, but an interrupt comes in that requires the CPU to wake up, that is about the worst case on this diagram, because we've already irrevocably started going to sleep. We're going to walk through, suspend, the sleep. Some of these are tremendously expensive activities, particularly at this level here. Walks into the off, and then immediately has the value asserted and turns back on. So you could look at high quality implementations of TF that are polling some of these things as they go through. There are things you can do in firmware to mitigate the delays a little bit, but ultimately we've been told to power on, we've gone through all these steps. That process can introduce some quite significant latencies. The time we take to get in and out of the states are, so in other words, it is not just the time it takes to exit the low power state that contributes to our latencies. We have to contemplate the point at which we've irrevocably entered into the state as the worst case latency from this kind of firmware. This will vary enormously depending on your architecture. But to put it in context, it is quite possible that some of those operations are expensive. If you are unpowering a substantial portion of the CPU, then you must flush L1 cache. And if you're taking a cluster down, you have to quite often flush L2 cache as well. Those are very, very expensive operations. And it might be that if you want to meet certain things, you will have to work with the people who implement. If you have particular latency targets, you might well have to work with firmware people to make sure that those operations are abortable or whatever else you need to meet certain latency concerns. But this can certainly introduce very long latencies. You have to bear it in mind. From the kernel point of view, obviously, like I say, there are some firmware quality things you can do to reduce these latencies. But from the kernel point of view, ultimately, low power and real time is about as fast as specified. If you cannot meet as fast as specified with all the power control systems turned on, you have to meet the specification. That's what real time means. You must meet the specification. So if you cannot tune these things and make them efficient enough to meet the specification, the only choice is to turn them off or constrain them. So in terms of low power states, you can be pushing into all the different firmware-based suspend processes. You can simply adopt the WFI instruction. The WFI instruction is a light sleep. It does some clock gating within the cores usually. It's actually microarchitecture defined, so exactly what it does is undefined, but in general, it is a clock gate within the system, but doesn't usually affect the power distribution. So it will reduce some dynamic costs, but it will leave the CPU sucking a certain amount of power. There are other constraints possible. You could look up the quality of service, in particular this CPU latency constraints has been put in. So in theory, when you are providing power systems to the kernel, you have to describe, it's usually in the device tree on an ARM system, the entry and exit costs to the different power levels in terms of latency. And on a non-real-time system, that's used to guesstimate when we're going to wake up and avoid going into deep sleep space unnecessarily. Because if you don't spend a long enough time residing in a deep sleep state, you don't actually save any power because flushing the L1 and 2 cache was more expensive than the amount of power you save by being asleep. So it's already being used, these kind of things, and it's already useful for power tuning that those values are roughly speaking correct. What we can do when we start a real-time activity is we can apply some latency constraints. Now, this is particularly applicable to multi-function systems, which can go into real-time modes and out of real-time modes. I hesitate to use phones as an example because there's not that much truly real-time stuff on a phone. But you can certainly imagine that when you pull up some kind of media playback, that you might want to inhibit certain states if you want to keep the Bluetooth audio to the phone running uninterrupted. And unfortunately, in our industrial control system, I just don't see that being changed dynamically. It's always going to be staring pane. You don't enter and exit different modes. So yes, there is an option to use these latency constraints, which basically prevent entry to certain idle states because it becomes too expensive, uses too much latency. You also have to think about CPU frequency controls, both the switching costs, as in how long it takes to change and whether there's a period during the change where the CPU stops running, and also whether you need to set an appropriate minimum frequency. Just as you can set latency constraints, you can also say, I require the CPU to always sit at this frequency. That's all I can really go into about power. Like there was some interesting comment pointing out that having schedulable interrupt handlers allows activities like little task packing to do its thing. So the traditional interrupt system, CPUs are simply assigned to particular CPUs. So the default on an ARM system usually is to throw them all at CPU 0, because that allows the other CPUs to go into deeper sleep states, and it's only CPU 0 that gets hammered with interrupts and has to wake up all the time. But other things are possible. And yes, the interesting point that's come up in the chat was this idea that having scheduled interrupt handlers allows existing power management mechanisms like little task packing to dynamically try to figure out where to put these things under different loads, which is very cool for power management. I haven't really thought about how that would apply to real-time systems. I mean, it is certainly true that by making things into threads, you do change a lot of the whole, way CPU affinity works, the alternative mechanism to CPU affinity, like control groups. So that does take us into interesting areas. But yes, power consumption reduction systems have latency, and you have to measure them against your specification is really the message here. So the last thing we want to look at is just this concept of best worst case performance, which most people with a real-time interest will have intuitive understanding of, and we'll also look at some of the tools that we have available to us to help with things. So best worst case performance, as fast as specified, not as fast as possible. Preempt RT slows the system down without dispute. Preempt RT costs much more. And most of real time, with that improving latencies, it's intrinsic to preempting that the cache gets blown out because we've changed the stack. And as the stack gets blown out, we increase our switching costs. That makes the system more expensive, even before you've got overhead. The actual act of switching tasks more frequently does hurt performance. And then on top of that, to make preempt RT work, we have more state to track. To make preempt without the RT work, we have more state to track than the states below it. To make voluntary work, we don't have very much state to track in the case of voluntary, but those cache costs are still going to eat into the overall system throughput. What we get with preempt RT, of course, is better worst case performance. It's what allows us to head towards specified. And it is amazingly difficult to hunt down graphs of exactly the real-time performance of a system. And that in part is for the various reasons that I've described, that it's based on the CPU frequency, it's based on the DDR technology, the whole set of things that says, how fast can I react to an interrupt? What is my longest period of latency? Is intrinsically built around the SOCs that you are constructing. So in other words, the only people who can usefully quote these kind of things tend to be SOC vendors. And certainly as Linaro, I'd like to stay out of it because I don't want to be saying this members goes really fast, because that just upsets all the other members. So this is a graph that we've borrowed from Red Hat, giving you a sense of the behavior of it. So it's basically comparing a real-time and non-real-time system. It's relatively old, actually. It's based on Red Hat 7, but there's no reason to see any differences. And do note that this is a logarithmic graph. And what it basically shows us is what we expect to some extent. Without preempt RT, the blue, most of the time, we react to things faster. We are able to take an interrupt and return to doing what we did before more quickly. In actual fact, it's a cyclic test, so it's taking an interrupt, switching threads, doing a relatively small activity that doesn't pollute the cache too much, and then jump back again. We are able to do that more quickly on a system that does not have preempt RT most of the time. That's why we get this dense, solid block of blue near the bottom. However, there are outliers, which is always at the top. And the outliers on this logarithmic graph are so much further away than the gap at the bottom. So this represents maybe 5 microseconds at best. This up here represents more than 1,000. So the outliers, the worst cases, the highest green you can usually see in this diagram sits around here at about 50 microseconds, and the plateau comes up here. There's a big chunk that clusters around 1,000 milliseconds. I don't know why it clusters there, I have to admit. And then even then, you've got outliers that could be 10 times longer than that. That's because we're tuned for the average case, and when we hit unusual cases, we are quite happy to spend the time fixing them. I'll also add that it was not, or I didn't double check whether this is preempt voluntary, or preempt none. I suspect it's preempt none because that's actually default for a lot of the Red Hat enterprise server stuff. So one of the reasons they had to have enterprise server and enterprise workstation back in the day was because they have different default tunings. So yeah, I suspect this might well have been against a preempt none. Overall, I'm going to show you a couple of the tools. I mean, this is basically a cyclic test tool, and cyclic test you will be looking at in the lab. So ultimately, this is something that you should generate for your platform to understand, even if you need to turn on preempt RT. If you have quite a relaxed specification, then this type of graph is acceptable. You know, I built real-time systems on Linux, and particularly with my background in multimedia, you can choose what your deadline is by the amount of data that you've back buffered and the size of buffers that you write to various places. You can't choose the vsync, but most of the other things you can choose. And so once you've seen a graph like this, you can say, yeah, I don't need preempt RT. Other systems, you do not have that luxury. Other systems, you look at that and you say, well, that means that I will have damaged something in these cases, so I must avoid it. So it's application dependent, and so drawing this graph is something you have to do on a case by case, on a stock by stock basis, possibly even board by board, depending on how you're configured. And making a decision based on it is case by case. It is to do with the specific real-time system that's being built. So some tools that can help us experiment in this space. So cyclic test is one of the fundamental mechanisms that we use to benchmark real-time systems and get this broad brush stroke of which preemption mode we think is going to be right for the system we're building. You've essentially built this. It was one of the exercises from last week. So it basically creates a thread that starts a defined number of measurement threads that run at real-time priority, shed 5 throws it happens. They are woken up periodically on a high-resolution timer, and we can then read the clock source and measure the difference between the programmed time and the actual wake-up time. And that is a relatively good measure of the latency that was observed by that specific instance. And then it's statistics after that. After that, we just run this in a loop over and over and over again, whilst we run a representative load. And that's the other reason these graphs are a little bit difficult, because what's the right representative load? So you have to run a load that is loading up the system call interfaces with enough interest to hit code paths that are going to generate latency. It is not simply burning CPU. You know, if you have a user space process that dominates the CPU alongside cyclic test, you will barely notice any change in the figures, or at least you shouldn't, because cyclic test is real time. It will always preempt those compute intensive threads. If those compute intensive threads are running in user space, they won't really contribute to latency. So in order for this to give you something interesting, something useful, you have to run some kind of workload. Now, classically, you'll look for some of the off-the-shelf benchmarks that allow, you know, as a SOC vendor, I would imagine you reach for off-the-shelf benchmarks, and that will give you a rough idea of worst cases. And you'll tend to lean, if you've got experience, towards fork-heavy workloads, so that you're hitting lots and lots of forks, which are one of the more expensive things, or you look for other bits of similar useful folklore of benchmarks that are likely to make real-time more difficult. So it works simple as this. You can fire it up. You can use our friend mlock all, which we remember from last week. You know what that's doing. We're saying we're going to an SMP, which means we run as many threads as there are things on the system, priority, interval, distance, and it will run through and it will produce some results which give you the minimum and maximum activation times. So another one that this one's sort of interesting. RT-app is useful for stimulating behaviors. It's mostly used by scheduler developers. And it can be used to generate synthetic loads of particular activation times to verify that the schedule is doing certain things. Like I say, it's very, very popular among power management engineers because it allows them to produce workloads that should produce particular power saving actions. And that's probably its biggest use in the RT space as well. If you have got systems where power management is involved, you can generate workloads synthetically that have similar to the specification of your real-time workloads, and observe the scheduler doing the right thing and verify that they get scheduled appropriately and everything else without having to construct the full system before you start. So if you're trying to figure out whether you have to hit minimum CPU freak, if you're trying to work out if you have to do certain things, you can actually generate synthetic loads to study what happens when you run them. So it's an option available to you. It is a very design-first methodology. If you're using RT-app to simulate things, you're looking at a very design-first methodology. Design-first methodology has a good number of reasons to do it in real-time systems. Just throwing things together and then finding out if you miss your deadline, that does happen. It definitely does happen in some real-time systems. But you're going as fast as specified. And it does help to understand the specification before you try and make something go as fast as specified. The rest of the little kind of silly tools I wanted to point out to you is a thing called RT-IRQ. And it's not because I expect you to use RT-IRQ for anything. It's because it represents a concept and a principle applied to audio workstations. So RT-IRQ is a simple service written, I think, by somebody with a strong musician bent that is there to try and pre-configure audio workstations. So it's designed to run on preempt RT kernels, and it will reach to and it will look for audio interrupt handlers and try to boost their priority above those of other interrupt handlers, so that the important task of the system, in this case being an audio workstation, gets done before other interrupts. The idea of this, as I've said, is it allows you to put the audio interrupt highest. It then allows you to put a strata of DSP tasks that are triggered by the audio interrupt next, and then it allows you to put the rest of the system. It's probably not going to be audio in very many cases. Pro audio is a relatively niche use case, but it's an interesting one because it's driven preempt RT. It was one of the first big users of preempt RT. Because although I've mentioned that low latency desktop is a good start for audio workstations, preempt RT takes you to the next level and puts you at that kind of I can run in a studio with confidence level. So this was a big early user of preempt RT. And that concept that you have to hunt for K threads that have been created by the rest of the system and tune will likely apply to other embedded systems. This will assume that you've decided to adopt preempt RT. So there've been some hints here. Preempt RT is both costly, may introduce latent bugs, and requires tuning to offer a significant benefit. So you may not decide to do some of these things. You know, you should not tune the priorities if you can meet the specification untuned, because untuned things like the networking stack is well balanced to get interrupts. You know, the more you tweak the priority of different threads, the more you move away from default tunables, and you might see some unexpected behaviors in some of the non-real-time parts of the system. But assuming that you have gone through preempt RT and you still need to find that last piece that is necessary to meet your specification, this is the last piece. It's applying tunings over the top from the defaults. It's not assuming the defaults are correct. So that's what this represents. It's not that you will use RT-IRQ. It's just a shell script. It's nothing terrifyingly complicated, but you are going to be reaching in, making some tunings, and then having to test that those tunings haven't done collateral damage somewhere else. The final item is ftrace. So ftrace was developed for the real-time kernel, and it was moved into the mainline kernel a very long time ago. It's a high-performance logging system that doesn't just track that things have happened, it also timestamps based on, I think, the highest resolution. I can't remember if it's shed clock or the regular clock source, but it's timestamped. And in any case, on ARM systems, there is no difference between those two clocks. It has this rich set of software events, which is mostly what we're going to be working on when we're working in real time. We can track all the scheduler's decision points. We can track entry and exit of all interrupt handlers. We can track when interrupts are locked and when interrupts are unlocked. We can track when preempt is enabled and preempt is disabled. It gives us an alternative way to view the system as opposed to cyclic test, which is a statistical view of the system. We can take a traced view of the system. We can run this IRQ preempt off, which will measure both the maximum time spent with IRQs locked or preempt disabled, because that will still happen on a preempt RT system. It will just happen much, much, much less than it does on a regular system. So that can be used against a workload to look for real-time hazards before they've happened. If you've got a specification that says my most significant problem is this one, this is the one that I have to react to all the time, and you can be running a background check to see have we ever locked for longer than our worst case, because if we have, then we can't guarantee we're going to meet the spec every time. So that's one option. The other thing, of course, is function tracing and function graph tracing. So the other thing that happens with real time is when you have to debug application latency. We've not talked about application latency much because it's not the kernel's fault, it's your applications. But when you miss a real-time deadline, the usual question that you need to debug it is, I think the system should have been handling my handler, it should have been running my real-time code, and it was doing something else. So the debugging question is, what was it doing when it missed the real-time deadline? It should have been handling it, and it was doing something else. And if that's the debugging question you have, again, ftrace, function trace probably is the best and quickest way to answer that question. Ftrace is quite complicated, so other than kind of giving you a sense that this is what it's used for, you know, the technique I would tend to apply is if I can ftrace the whole system and it still works to specification, because ftrace has costs as well. If I can ftrace the entire system with a function trace and the system will survive that, then that's what I would do. I would run it full wide. I would then find out when I missed my real-time deadline and find out what it was running instead. That would give me essentially the kernel functions or user space that it's running. So I'll either know the user space task that's running or the kernel, and it will give me the thread that's involved. And then I can dig deep. It shouldn't be in user space, because if you missed the real-time deadline in user space, particularly if it's an interrupt handler, it should have preempted. That disappears a little bit with preempt RT because so much more is now schedulable and not running in kernel. But yeah, the tracer is enormously powerful in finding out what you've missed, and you've got graphical tools that lay over the top. So it's definitely worth looking at for all aspects of real-time debug. I think for this audience, I'm not going to go deep on this. Basically, it's comparing mainline Linux, preempt RT, and a couple of real-time operating systems. And the major differences that crop out are this strong distinguishment between real-time and normal tasks on the Linux versus non-Linux view of the world. And of course, the difference, the fact that for a lot of other aspects, Linux with preempt RT shares a lot more in common with VxWorks and QX Neutrino. It is designed along similar design patterns, the full preemption, the priority inversion protection, the minimal interrupt locking. So VxWorks and QX Neutrino classically will allow things like interrupt locking, but because everybody who ever worked on them knows it's a real-time operating system, they tend to intrinsically pick very short windows. Whereas Linux's history as a server operating system means that kind of mindset wasn't present when various of the locks were being contemplated and added. So I think I have 5 minutes left before the nominal end of the session. I just want to talk a little bit about where in Linaro I've come from. I've mentioned I chose to deliver this to members now because PreemptRT is on its way to the kernel. I work in the services group at Linaro, and your members, which means you all know about the collaborative side of Linaro, where you engage with Linaro to collaborate on things that other members find useful as well. Services is all about people who want to work on their own products. Now, sometimes that does involve collaboration with others. It's in the DNA of Linaro to collaborate, to leverage open source is what we're all about. But we do provide services that companies can use to target their specific priorities. So whether that's forward enablement, looking at some of the security features, it's turning features on ultimately is what we particularly excel at. So if that's what you are interested in, if it's a gap that you have in any of your projects, then do bear in mind that Linaro isn't just a place to develop the shared technologies. We can help you enable them as well. Obviously, our training and education services are very close to my heart. I am the training manager at Linaro as one of our most heavily used trainers. We have other trainers incidentally, it's not just me. So yes, we have these things. If you are working for club and core members, club and core members do receive a certain amount of opportunities to take training at no additional charge. Group members, project members, our training services are chargeable as they would be for people outside of Linaro. But either way, whichever group you come in, we have things like training catalog to let you know what courses we offer. There are some courses down the right there, but we have a wide range of courses, and I'm going to say growing all the time, although we haven't got anything in development at the moment. So there is nothing pending to add to the catalog in the short term. And then finally, Linaro developer technical support. That's a service available to all members. So if you're in the room today, you have access to this service. And the best way to describe it is we stand behind the work of Linaro. The whole of Linaro. So if Linaro's been working on it and you need help either understanding more about it to leverage it in your designs, if you don't want to use our services, you can contact LDJs. We'll still help you get it up and running. We won't type it for you, but if there's knowledge and if you have questions about how to make it work best on your platform, we're there to help you. And we can reach behind to, we're not just my team, we are connected to the rest of Linaro, and we will go and find the right people to talk to about your problem and get you the answer. That's what we're for. Some summaries of how to get support from Linaro. So simplest one is support@linaro.org. You can also find us at support.linaro.org from your web browser, and we do our very, very best to keep us well set up to be discoverable on the web. So if you type Linaro support into a search engine and you are not, or we are not in the top 5 answers, I would be very, very disappointed, and you could perhaps even raise a support ticket about that. We can't always fix these things. Search engines are not within our control, but we do usually expect, Linaro being such an unusual word, Linaro support should rank you very highly and take you to a site that repeats this information for you. So that gets us to the end of today, apart from the lab session. So the only real thing I wanted to say about the lab session is we have set things up so you can run a PreemptRT kernel on the system and run things like Hackbench. So we've deliberately included some benchmarks which may allow you, depending on your hardware, to observe a slowdown as a result of turning on PreemptRT. As I said, it has an overhead. What we cannot show you in the labs is any benefit from PreemptRT. This is the elephant in the room. Simulators don't effectively allow you to measure RT performance because they are hosted on your desktop non-RT kernel, and the virtual CPUs from the simulated machine are competing for other tasks on your CPU, like managing your mouse and drawing pictures. So the latencies that you observe inside the virtual machine that you have been working on are not just influenced by its own kernel, they're also influenced by delays in the host kernel. So the only meaningful way that you can really explore PreemptRT is to turn it on your own hardware. So this is the cheapest thing I could come up with for you to try and turn this on, and it's based on a trick around trying to match version numbers so you get the minimal merge conflicts. If you're experienced resolving merge conflicts, go straight to the production version. But this is the idea that if you have a board, turn it on, see what works, see if you get config, debug sleep atomic problems. That is the most important single lab activity you can do after learning about preempt RT, is to turn it on and see what happens on your platform. So with that, I get to the end of today. I've got the slide up with support@linaro.org up as a reminder. I have run slightly, I wanted to have a little bit more time for questions at the end before we got to the end of the scheduled slot. But to be honest, if anybody wants to stay on and ask any questions, you are very, very welcome to do that. But other than that, thank you very, very much for joining me. And like I say, I hope you enjoy playing with the various real-time features.